So, good afternoon. Today we'll go through the petrographic study of a sedimentary rock, that is sandstone. So, if we look at the classification of clastic sedimentary rocks, that means those sedimentary rocks which have their origin by fragmenting a pre-existing rock, that means mainly physical weathering is responsible, mainly physical weathering. That doesn't mean that it does not occur by chemical way or by biological way, but whatever may be the processes by which a pre-existing rock becomes fragmented, uh, it breaks down into some smaller pieces, and those pieces are carried out by some transporting agents, and after that they are deposited in a basin, and with time, by suffering diagenesis and other processes, they will solidify, lithification occur, and they form the clastic sedimentary rocks. So as the name suggests, and then deposited and solidified. So a very basic classification of all sedimentary rocks, based on the type material which is deposited, by differing uh, types of natural agents by which they are carried and deposited in a basin. On this criteria, we can divide the sedimentary rocks into two groups, and these sedimentary rocks are fragmented by mainly physical and chemical weathering processes, but biological organisms, they also play a huge role on weathering of pre-existing rocks. So after fragmentation, those fragmented particles, they are carried either by river or by wind or glacier or different kinds of oceanic currents. Sometimes volcanic explosions also take place, and thereby the fragments move from one place to another place. Now the fragmented particles, they are either done and move as clastic sediments, or they may be completely dissolved and lost their chemical identity. That means from one chemical component to uh, they change to another chemical component, and they will dissolve into a aqueous solution, thereby formed the chemical sediments. Now when suitable condition comes from this uh, chemical solution, precipitation occurs, and this precipitation from the direct solution is known as orthochemical sediments. Apart from that, we know that in the aqueous medium there are also some biological bodies. After their death, the hard parts, they are the biological material, biological entity, so they also deposited as biological sediment. Some parts of the biological material also become soluble in the solution, and there are some bioclastic sediments, that is the shells or hard parts of the organisms, they becomes fragmented and reworked occur. So there is a continual reworking and change from direct biogenic sediment to bioclastic sediments, or bioclastic sediment to biogenic sediments. And the other group, that is the simply the purely fragmented material, the terrigenous clastic sediments that came directly from the pre-existing host rock, that is the minute fragments of a pre-existing rocks, they become fragmented and deposited into a basins. So two broad groups: one is the pre-existing rock, the miniature version of the pre-existing rocks in terms of different small size particles, that may be sand, that may be clay, that may be pebble, cobble, or boulder size particles. They are deposited uh, after fragmentation. And the other types where chemical process is the main process by which the mineral constituents, they lost their chemical identity, they form in a different types of chemical constituent, and thereby soluble in the aqueous medium, and in suitable condition from that solution, the materials or the minerals precipitated in forms of sediments. So two types, one is chemical, another is clastic. And the other types within the clastic is the pyroclastic that forms during some volcanic eruption. Now, if we look at the sediment size, that means sediment grain size, a simple classification of terrigenous clastic rocks and sediments uh, size is done, and mainly here we follow the Ardeno Wentworth grade scale, and according to the sediment size different name of the rocks are given. So in the first or the coarser part, coarser detrital fragments higher than sand size, that is the gravel size. For them, a generalized term is rudite is usable, and you may already aware that within this rudite, the conglomerate and the breccia are the two different rock types which clubbed under this rudite. Uh, Next group, in which the sediment grain size falls between 2 millimeter to 0.0625 millimeter, that is the sand size particles. And the rock name, previously it was called arenite, but nowadays uh, apart from arenite it is more generally called sandstones. And the lower size of sand, that is the silt size, that is known as siltstone, and mud or clay size particles, they are known as mudstone or lutite. So here you can see simply this classification of sedimentary rocks or nomenclature of sedimentary rocks is purely based on the sediment size. Now, for the purposes of this general classification, we assign the rock or sediment name where the more than 50% of the particles are falling in this range. So whenever we call a rock rudite, that indicates immediately that greater than 50% of the grains, sedimentary grains, are of gravel size particles. Whenever we call a sedimentary rock as sandstone, that means greater than 50% of the sedimentary particles are of sand size that falls within this diameter range. Now coming to the sandstone, so you can well understood that whenever we use the term sandstone, that most of the sedimentary particles, most of the detrital fragments, they are of sand size sand size particles. Now most sandstone classifications are based on the composition of the rock, that is uh, by which material, by which mineral constituent the sedimentary grains are composed of, that is the mineralogical composition of the sedimentary grains. Although there are many different types of classifications are there, but the most usable or most used, most accepted classification globally is the dot classifications, which is proposed in the year 1964. And after, in 1987, Petitjohn and its co-workers, they modify the earlier proposed dot classification. So nowadays it is proposed as dots classification modified by Petitjohn's Petitjohn and his co-workers. Now in this classification, the classification is based on purely on the relative proportions of different constituents. Now whenever we are going to study a sedimentary rock, particularly a clastic sedimentary rock, a clastic sedimentary rock is made up of three constituents. First, it is the framework, that is the larger size detrital particles or the larger size clast, which makes the framework or makes the structure of the rock, that is known as framework grains. And those framework grains are of different mineral constituents are there. The main framework material or the main framework mineral which is found in the detrital sedimentary rock or particularly in sandstone, those are of quartz, feldspar, rock fragments, and some other minute constituents. Sometimes we get muscovite, biotite, some galena, and other constituents, mineral constituents are there. But these three are the most common, and depending on the relative proportion of these three framework particles, different names of sandstones are proposed. Now, as the name suggests, that framework, that means it forms the frame, it forms the basic structure of the rock. So whenever these sediments, these larger size electrolyte particles forms the frame to hold or to bind these framework grains, we need a relatively finer size particle which is able to mix with the larger size framework grains and hold them or bind them in a solid structure. Say for example, you may observe construction of a building or construction of a wall. So here for construction of a wall, we require some bricks, and we may arrange those bricks in a vertical sequence in a different manner according to our choice and make a vertical structure or make a vertical wall. But if we did not give any kind of binding material to those bricks, then with slight force acting on those wall, the structure, the vertical structure made up by those bricks, that may collapse. So we require a binding material which can hold the vertical structure made up by those bricks. So that is why we mix a relatively finer size mixture that is made up of sand and the cement, and that mixture is used in the gaps, in the pores of those bricks, so that they can attach or they can hold all the bricks together and make the wall as a rigid substance, as a solid substance, so that with slight force applied to that wall does not collapse. That wall may remain as it is. So those sand and cement mixture as a binding material for those bricks. Similarly, in case of clastic sedimentary rocks, apart from the framework grains which makes the frame or basic structure of the rock, we need a binding material, and that binding material must be fine grained compared to the framework grains. So this particularly fine grained binding material in case of clastic sedimentary rock is known as matrix. So the framework grains, they constitute the frame of the sedimentary rock, and the finer sized mixture, that in case of sedimentary rock we call them as matrix. This matrix hold all the framework grains together, and this matrix is the responsible factor or responsible part for which the detrital grains may attach or may stay with each other and forms the sedimentary rock. So this is the main function of the finer size particle bind the sediments. But apart from matrix and the framework grains, there is another constituent found in the clastic sedimentary rocks that is known as cement. And this cement, how it is formed, how did you identify or how did you separate them from matrix, that I will come into some later slides. But the cement is the main responsible agent which produce the hardening to the sedimentary rocks. That means cement helps in lithification. So until or unless there was no cement in the clastic sedimentary rock, that detrital or clastic sedimentary rock will not be uh, so hard or so lithified such that we observed in our surroundings. So that may be a loosely bind sedimentary rock, not rigid enough, not solid enough. So cement is the main lithification agent for a clastic sedimentary rock. Now, as I already told you that the main framework grain found in nature is the quartz, feldspar, and rock fragment with some accessory other minerals. But in theoretically, all the mineral variants which we found in the natural rocks that may present in a clastic sedimentary rock. So in a clastic sedimentary rock, you may even found a diamond. That is theoretically possible. In a sedimentary condition, a diamond can be fragmented and transported by natural agents and deposited in a basin, and from that a sandstone or other clastic sedimentary rock can form. But according to the available rock types in the surfacial conditions of the earth, quartz, feldspar, and rock fragment, these are the most readily found minerals in most of the igneous and metamorphic or sedimentary rocks, and thereby these three are the most framework grains which we found in the clastic sedimentary rocks. Although all sorts of possible mineral composition they may be present in a clastic sedimentary rock. So coming to the most readily found plastic sedimentary rock, that is quartz. Now quartz we can very well aware about its physical and optical properties, so we can easily identify quartz. It is very hard, um, lacks any kinds of cleavage, its color is almost colorless. We did not get any streak in our streak plate, and in optical properties if we concern, that is they have a low to moderate RI, almost colorless, and low birefringence. Interference color is also in the first order. So thereby you can easily identify quartz both in hand specimen or in microscope in a sandstone. And if we look at the Bowen's reaction series, we found that the quartz is the mineral which is the last formed minerals. Among the last formed minerals in the Bowen's reaction series, quartz is one of them. So that means in the last phase of solidification of a magma that is more close to the surfacial pressure temperature condition, quartz is crystallizing from a molten material, from a magma. So that is why when quartz rich rocks, any kind of rock, it may be igneous or it may be metamorphic rock, they are exposed to the surfacial pressure temperature condition, they becomes more stable than the earlier formed, earlier crystallizing minerals in the Bowen's reaction series, because the change in pressure temperature condition from the subsurface condition to the surface condition is very minimum for quartz and other minerals which crystallize in the last phase of Bowen's reaction series. So that means they are forming, they are crystallizing more close to the surfacial pressure temperature condition. Now if we look at the average sandstone content, average quartz content in a sandstone, we found that uh, most of the sandstone of the world that constitute about 65% quartz within its framework grains. So among, if we consider all the framework grains as 100%, among these 100, only quartz constitute about 65%. But there are some sandstones in which practically it is composed of 100% of quartz. So all the framework grains in those sandstones are entirely of quartz grains. Now among the quartz, there are various types of quartz we found in natural deposits. Depending on the number of crystals within a single quartz grain, we can divide the quartz grain into two types. The first one is monocrystalline quartz, where the entire quartz grain is composed of a single crystal, and the other types is known as polycrystalline quartz, where the entire quartz grain is made up of two or more crystals. Now, polycrystalline grains can be again divided into two groups, one in which the number of crystals is restricted within 2 or 3, and the other type of polycrystalline quartz where the number of crystals is greater than 3. So all sorts of possible quartz types, both monocrystalline and polycrystalline, that we gain that we found in the sandstones. And the polycrystalline quartz, particularly this type where there are a number of more than one number of crystals within a single quartz grain, and the boundaries between individual crystals within a single quartz grain that can be identified clearly within the petrological microscope. Again, quartz grains can be divided uh, depending on its type of extinction, but here the quartz grains are particularly uh, taken into account, the monocrystalline quartz, depending on the type of extinction. The first type, which is known as non-undulatory quartz, where the entire quartz grain extinct at a single position. So whenever under petrological microscope we observe a quartz grain, and with rotation of stage we found that at certain condition the entire quartz grain becomes dark, and that darkness or that extinct position occurs at a single position of the with rotation of the microscope stage. But there is a other type of quartz found in nature that known as undulatory quartz. So here extinction occurs not uniformly. Extinction does not occur uniformly throughout the grain. Rather, the extinction sweeps entire the grain. That means different parts of the single quartz grain becomes dark with rotation of the microscope stage at different points. So it looks like a wavy manner of extinction. So often this undulatory extinction is known as wavy extinction. That means different parts of the single quartz grain extinct at different times. Now, there are some features found in the quartz grains which are provenance. That means from which type of rock material those quartz grains are derived. Firstly, if a quartz grain derived from a volcanic igneous rock, then we found that in a sedimentary rock, in the sandstone, the quartz grains are mostly monocrystalline and showing unit extinction. That means non-undulatory extinction. So non-undulatory extinction is also known as unit extinction, and no inclusion is found within those quartz grains. So if these kinds of quartz, that means mostly monocrystalline quartz having unit extinction and without any inclusion, is found within a sandstone, then we may infer that that quartz grain is coming from a volcanic igneous source rock. But if the quartz grain coming from the hydrothermal vents, then we found both monocrystalline and polycrystalline quartz, but those quartz grains characteristically contains numerous inclusions. So if there are numerous inclusions found within the quartz grains, we may infer that it is coming from hydrothermal vents. Similarly, if we found polycrystalline quartz mostly, that indicates that the quartz grain suffers a strained condition, that it suffers some kinds of metamorphic condition where it suffers a higher pressure, higher strain condition, so that it will strain and shows these kinds of elongation or preferred orientation of the quartz grains. So instead of a circular um, nature of a quartz grain, we get a somewhat elongated oriented quartz grains having more than one crystals within a single quartz grain, that is polycrystalline. So depending on the different properties of quartz grains, you can see that different source rock can be inferred. Monocrystalline quartz with undulous extinction and polycrystalline quartz are both less stable than the unstrained, that means non-undulatory extinct monocrystalline quartz. So that means undulous extinction in a quartz grain, if shows, that means it is in a strained condition. So that means it is not stable in the superficial pressure temperature condition. Similarly, if a quartz grain shows more than one crystal, that means it is a polycrystalline. So with slight transportation, with slight pressure, that quartz grain have a tendency to break from those crystal boundaries, and it forms numerous fragments. So if we consider the stability of the quartz grains, of the different varieties of the quartz grains, the monocrystalline non-undulatory quartz are the most stable grains, whereas monocrystalline undulatory and polycrystalline quartz, they are less stable. As a result, during transportation, if these quartz grains suffered a prolonged transportation, in this prolonged transportation, the unstable grains, that means the monocrystalline undulatory extinct quartz and the polycrystalline quartz, they are selectively removed during weathering. That means they are fragmented and further uh, formed smaller detrital particles. That means their size may be reduced even, but the monocrystalline non-undulatory quartz at their most stable among the all other quartz that we found mostly in the sedimentary rocks, which suffer a prolonged transportation and after that they will deposit. So if we found that in a sedimentary sandstone that contains about same amount of monocrystalline non-undulatory quartz, at the same time same amount of monocrystalline undulatory quartz and polycrystalline quartz. So that means both stable variety of quartz and unstable variety of quartz, they are almost present in equal quantity, equal amount. That indicates that the sediments, they does not suffer a prolonged transportation, so they are deposited immediately or very close to their source rock. But if those minerals suffers a long transportation path, then during this transportation, due to different kinds of weathering process, the unstable varieties of quartz, they are selectively removed. So monocrystalline by polycrystalline quartz, if we do a ratio of monocrystalline by polycrystalline quartz and unstrained by strained quartz, that will give a maturity index for the sedimentary rock or for the sandstone. That means if we get more stable varieties of quartz, that means it suffers a long transportation, and with increasing pressure, those grains are not easily broken up. That means the rock is more or less stable. But if a sedimentary sandstone is composed mostly of unstable quartz grains, with increasing pressure, with increasing diagenetic pressure or overburden pressure, the grains may be fragmented even after the formation of the rock. Now, there is another indication to know uh, about the source rock depending on the relative abundance of monocrystalline undulatory quartz as well as the polycrystalline quartz having 2 to 3 subgrains, 2 to 3 crystals, and the polycrystalline quartz having greater than 3 crystals. So all these four varieties, if we plot them in a diamond diagram, in these corners, here you can see the polycrystalline quartz having 2 to 3 crystals, here the polycrystalline quartz having greater than 3 crystals, here the monocrystalline quartz having non-undulatory extinction, and in this corner the monocrystalline quartz having undulatory extinction. Now if all the naturally variants or naturally found sandstones are when analyzed and they are plotted in this diamond diagram, it was found that the sandstones which having mostly the polycrystalline quartz having 2 to 3 crystals and mostly non-undulatory monocrystalline quartz, they came from the plutonic source rock. So all the sandstone in which the quartz grain comes from plutonic igneous rocks, they are plotted or in this region. Whereas sandstones which have all sorts of variation of quartz grains, that means both monocrystalline non-undulatory quartz and monocrystalline undulatory quartz with different types of polycrystalline quartz are present. If when they are plotted, it was found that they come from the middle and upper rank metamorphic rocks. So high grade metamorphic rocks, from that we get these sorts of variables. And lastly, the the sandstones which is rich in monocrystalline undulatory quartz and polycrystalline quartz having greater than 3 crystals, they came from the low rank metamorphic rocks. So you can see, when only the different varieties of quartz grains within a sedimentary rock, they are plotted in a diamond diagram, we can clearly get an idea about the source rock of that particular sandstone from which the quartz grains are coming off. Now coming to the next abundant mineral constituent which we found in nature, and that is feldspar. The feldspar contained in sandstone averages between sandstones found in nature, in which the feldspar content may reach up to 50%. So almost 50% of the feldspar or 50% of the framework grains within a sandstone, those are made up of feldspar. Now the mechanical stability of the feldspar grains, uh, feldspar is less stable because it has two sets of cleavage. Also, its hardness is lower than feldspar. So the mechanical durability of feldspar is far lower than quartz, and that is why feldspar leads to more disintegration or more fragmentation than a quartz during the transportation processes. Now, apart from the physical durability, the chemical stability of feldspar is also lower because the feldspar has a tendency to react with the aqueous condition, and in this case the feldspar is hydrolyzed. That means H plus ion displaces other ions. So chemical alteration of feldspar also occur in nature, and during this chemical alteration, uh, the feldspar alters to other kinds of clay minerals also. Now we know that in nature there are different types of feldspar, such as potash feldspar, orthoclase feldspar, microcline, plagioclase feldspar. Among these, the potash feldspar, orthoclase, and microcline, they are more commonly found in the sandstones rocks compared to plagioclase feldspar, because the potash feldspar, and if you consider all these variants of feldspar, among all these potash feldspar is most stable, and that is why we found potash feldspar mostly in the sandstones. Now, why potash feldspar is so much abundant in sandstones? Because of its durability. Potash feldspar has a greater chemical stability than plagioclase, so the plagioclase feldspar has more tendency to alter during the weathering processes. Not only that, potash feldspar is also much more common in the continental basement rocks, such as the granites or gneissic rocks. But there are certain kinds of sandstones in which the feldspar is coming from the weathering of some island arc systems. So when the framework grains are weathered from an island arc system in an island arc deposit, The plagioclase feldspar are highly abundant. So if weathering of island arc occurs and they fragmented and deposited in a basin, in that particular deposition, plagioclase feldspar is generally higher in concentration compared to potash feldspar. But in general, as the durability of potash feldspar is higher than other kinds of feldspar, also potash feldspar is more abundant in all the superficial rocks, particularly the continental basement rocks like granite, gneisses. So it is obviously that we get more and more potash feldspar in a sedimentary deposition in a sandstone. Now, apart from the suitable source rocks, the feldspar content of a sediment is largely controlled by the rate of erosion and the climate. A humid climate in the source area that promotes more feldspar destruction because of the dominant chemical weathering processes. But in an area which have a arid condition, that means dry condition, in those places, we found more and more fresh feldspar that will survive the physical weathering processes. Now, from our previous weathering classes, we already aware that in a humid condition where there is ample amount of water vapor in nature and where there is a higher amount of precipitation, in those places more and more chemical weathering occurs. But in a dry, arid condition, their physical weathering is the dominant process of weathering. So as physical weathering is occurring in the dry, arid climatic conditions, the feldspar is only suffering the physical weathering processes, and thereby when they are deposited, the feldspar are not chemically altered. So we found fresh feldspar grains in the sedimentary deposition. But in case of a humid climate where there is ample amount of water vapor and precipitation, there not only physical weathering is going on, but apart from that, the feldspar grains also suffer chemical weathering. So due to the chemical weathering, as I already told you, that feldspar becomes hydrolyzed and they form some clay minerals. So we found some altered feldspars, and often the feldspar grains are completely altered to the clay minerals. So feldspar grains entirely lost its identity. So depending on the climatic condition, the availability as well as the size and the alteration of feldspar is also depending. So rapid erosion in high relief area will produce feldspar grains in spite of humid climate. Alkali feldspar, more sodic than albite 50, are generally of volcanic origin. So again, the composition of feldspar grains helps us to identify the source rock. Alkali feldspar more potassic than orthoclase 88. They are derived from plutonic and metamorphic source rocks. So depending on the relative composition, we may also get an idea about the relative source of. Apart from feldspar, the third abundant framework grains found in the sandstones is the rock fragment. So as the name suggests, rock fragment, that is, it is a miniature version of the pre-existing source rock. So as a whole, within these framework grains, the all the pre-existing minerals of the host rocks, they are present in minute amount. Suppose the pre-existing host rock, it consists of three minerals, say for example A, B and C. So the host rock composed this by these three minerals. Now when this host rock fragmented and form minute sand-sized particles, in those minute sand-sized particles we also get the evidences of these three minerals. That means in these small fragments, in this small sand sized fragment, we also get A, B, C minerals. That means it is the miniature version of the original host rock. So for this reason, rock fragments are better provenance indicator, as in these rock fragment grains we get almost the entire mineralogical composition of the host rock. But if we get a quartz, say for example, if we get a quartz, that quartz may came from different kinds of rocks. That quartz may came from a igneous rock, that quartz may came from a metamorphic rock, that quartz may came from a sedimentary rock. And you already know within igneous, metamorphic and sedimentary rocks there are different kinds of rocks. So similarly, the feldspar that may come from different kinds of rocks. But if we get a rock fragment which already host or which already have all the pre-existing or all the minerals of the pre-existing host rocks, so simply by observing the rock fragment, we may came to infer or we may came to know about the original scenario from which that particular fragment is weathered and transported. Now, the common rock fragments found in the sandstones, those are of mudstone, shale, chert, slate, phyllite, and mica schist. Now, rock fragments in sandstones, they are most commonly found of fine-grained sedimentary rocks such as the mudstone, shale, and chert, or some low-grade metamorphic or metasedimentary rocks such as the slate, phyllite, and mica schist. Now, many rock fragments are unstable, but these rock fragments are characteristics of certain particular sandstone types. Rock fragments generally derived from supracrustal rocks undergoing rapid uplift and erosion. Mountain beds and volcanic areas supply large quantities, whereas continental and granitic basement supplies less quantity of rock fragments. If a rock fragment comes from a plutonic rock, we may find a coarsely crystalline fragment having large size crystals within the rock fragment. Whereas the volcanic igneous rock, they will form fine grain and contains lots of plagioclase feldspar layers in those rock fragmented material. So depending on the size of the uh, crystals within the rock fragment, we may also get an idea about the source rocks. Next, minute minerals apart from the quartz, feldspar, and rock fragment. I already told you that these three are the main framework constituents which we found in sandstones. But apart from these three, the other mineral constituents uh, also found in nature, that is the micas and clay minerals. Mica are the seed silicates or phyllosilicates, and they are particularly common in the matrix portion of the sandstones. But apart from matrix, mica group of minerals or these seed silicates are also found as framework grains, that is composed, that is having the sand sized. Um, they are also found. Now, as you know that mica group of minerals, they are lath shaped, they are flaky, so they are very light in specific weight. So mostly the seed silicates or phyllosilicates, they are transported a long distance, and often they are removed very easily by the wind blown sediments. So you may get a size differentiation if you get quartz feldspar rock fragments along with mica, because that depends on the specific gravity or relative weight compared to its volume. So the quartz grain having this size, the weight of this quartz grain may be equal to the mica sheet or mica flakes of this size. So, and we know that deposition occurs depending on its weight. So you may get different sizes of framework grains depending on their specific gravity. So The with smaller sized quartz feldspar rock fragment grains, you may get larger size mica group of minerals. Apart from mica group of minerals, clay minerals are also found in sandstones, and those clay minerals are present both in the matrix as well as in sometimes as in the framework grains. These clay minerals have their origin both by detrital and orthogenic. Detrital means they are already present in the host rock, and from that host rock they are weathering and eroded, and later they are deposited simply due to their specific gravity. So that is physical, mainly physical weathering process. But the other type, that is orthogenic clay minerals, these type of clay minerals deposited from a chemical solution. So they are chemically precipitated clay minerals. Apart from mica and clay minerals, heavy minerals are also found in nature, and these are accessory grains found in sandstone, and their abundance is almost less than 1%, and these are mostly composed of or mostly the silicates and oxide minerals, particularly the apatite, epidote, garnet, staurolite, tourmaline, zircon, magnetite, hematite, ilmenite. These are the some examples of heavy minerals. Now, the specific gravity of these heavy minerals are far greater than Canada balsam as well as greater than quartz and feldspar. Most of the heavy minerals, the previous mentioned these heavy minerals, they have the specific gravity above 2.9, whereas the specific gravity of quartz and feldspar is about 2.6. So again, if we get heavy minerals and quartz feldspar grains as framework grains, there will be a size differentiation. So quartz grains, as they have lower specific gravity, they have higher sized, whereas at the same condition, if we get a heavy mineral, that will be of far lower size compared to quartz and feldspar grains. Now, if we look at the common heavy mineral, we find apatite, biotite, hornblende, monazite, tourmaline, zircon. These came from the acid igneous rock, whereas fluorite, garnet, muscovite, topaz, monazite, they may came from granite pegmatites. Minerals like augite, diopside, hypersthene, magnetite, chromite, they came from basic igneous rock. Andalusite, garnet, staurolite, sillimanite, epidote, they came from metamorphic rocks, whereas barite, iron ores, rutile, zircon, they came from reworked sediments. So you can get an idea of the source rock depending on the heavy mineral assemblage. So here, not a single mineral will give you an idea of the host rock or the provenance rock, the source rock, but instead here we consider the heavy mineral assemblage, because a single type of mineral may come from different source rock. Say for example, here you can see garnet. Garnet may came from granite pegmatite, that is a igneous rock, whereas garnet may also came from a metamorphic rock also. But if you consider the assemblage of heavy minerals in these two types, you can see the assemblage is entirely different for these two types. If garnet comes from a granitic pegmatite, that is igneous rock, then along with garnet we found in the sandstones fluorite, muscovite, topaz, tourmaline, and monazite. But if garnet came from a metamorphic source rock, then along with garnet as heavy minerals, we may get kyanite, sillimanite, zoisite, epidote, andalusite, these heavy minerals. So depending on the heavy mineral assemblage within the sandstone rocks, we may also get an idea about the source rock of for that particular deposition. Now, as I already told, for a clastic sedimentary rock, it has mainly three constituent parts. One is the framework grains, that is allogenic, that is directly came from fragmentation of a pre-existing rock, and these forms the frame or the basic structure of the sedimentary rock. Within these framework grains, there are finer grained mixture that is known as matrix, which holds or binds the framework grains, and there is some chemical precipitation occurs from the pore fluid that is known as orthogenic deposition. So within the pore space, within the void space of framework and matrix grains, there are some fluids, there are some chemical solutions, and from that chemical solution, if precipitation occurs in a suitable condition, that is known as chemically precipitated sediment or known as cement. And this cement is the main agent which lithified or which solidified the sandstone or which solidified any kinds of sedimentary rocks. Now, depending on the relative abundance of framework grains, a sandstone may be grain supported. Here you can see mostly it is composed of framework grains. Only in the pore spaces minute amount of matrix is present, and the framework grains are in contact with each other. Whereas there is other types where you can see the framework grains are floating within the matrix. That means a huge amount of matrix is there and the framework grains are isolated from each other. So this type of sandstone is known as matrix supported. So when the sandstone is matrix rich, framework grains are separated from each other by matrix. They are floating in nature. It is called matrix supported. When framework grains are in contact with each other, less amount of matrix is there, it is known as grain supported. So here you can see the finer grains between major clast. These are the matrix. The crystalline precipitation from the pore fluid, that is known as cement. In grain supported sandstones, the grains are framework grains are touching with each other, matrix percentage is very low. Whereas in matrix supported sandstone, matrix are the most in amount, framework grains are floating in nature, it is known as matrix supported. Now coming to the classification scheme or classification diagram that is proposed by Dot in 1964 and modified by Petitjean and his co-workers in 1987. So it's a simple triangular diagram in which the sandstones are initially divided on the basis of matrix percentage. So first we divide the clastic sedimentary rock on the basis of their grain size, that is a textural classification, and depending on the grain size we group them in sandstone, rudite and lutite in these three groups. After that, if we focus on more on sandstone, firstly we clubbed or we grouped sandstones into two groups depending on the matrix percentage. So in sandstones where the matrix percentage is up to 15%, if we consider all the components of a sandstone, that means uh, the entire framework, matrix and cement that made 100%, then within that 100%, if matrix content is up to 15%, sandstone as arenites. So arenite is a group of sandstone where the matrix percentage is below 15%, whatever may be the framework grain composition. Now, the matrix percentage when becomes higher than 15%, in that case, where the matrix percentage is restricted up from 15% to 75%, then we call them as Wake group of sandstones, or we call them simply Wakes. Above 75% matrix percentage, we don't call them as sandstones, then they are classified into a separate group of sedimentary rock that is known as mudstones or claystones. So up to 75% matrix, we call them as sandstones. Now from 0 to 75% matrix percentage, there are two groups. In one group from 0 to 15%, these are known as arenites. The second group, in which the matrix percentage varies from 15% to 75%, we call them as Wakes. Now, after grouping the sandstone into arenites and Wakes, depending on the relative percentage of matrix, then we came to focus on the relative percentage of different framework mineral grains. And we plot a triangular diagram. In this triangular diagram, in three corners we plot quartz in one corner, feldspar in one corner, and rock fragment in the other corner. So the presence of quartz in this corner means in this pointed portion, the percentage of quartz is within the framework grains is 100%. In this point, feldspar is written means at this particular point, the feldspar content among all the framework grains is 100%. So the rock is composed entirely of feldspar when we consider the framework particles. Similarly, here all the framework particles are of rock fragments. Now, depending on the relative abundance of these framework particles, different names are proposed. When the relative proportion of quartz among all the framework grains is greater than 95%, that means the entire rock is composed of a single type of framework grain, and the matrix percentage obviously is less than 15%, the rock is known as quartz arenite and it falls in this region. Now, when the arenitic sandstone rock is rich in feldspar, but the feldspar content is greater than rock fragment or lithic fragment, then it is known as arcosic arenite or simply arcose. Similarly, when the rock is rich in lithic fragment or rock fragment and the proportion of lithic fragment is greater than feldspar, then it is known as lithic arenite. And obviously, the matrix percentage should be less than 15% here. And here you can see that there is an intermediate portion where the feldspar content is um, greater than feldspar content is less than 25% and the quartz content is about 75 to 95%, and the feldspar content is higher than lithic fragment. That group is known as subarcose. Similarly, this right side portion, the rock fragment is less than 25% and quartz is about 95 to 75 percentage, and the feldspar content is higher than feldspar. This portion is known as sublithic arenite. So you can see this classification always the arenite group of sandstones are classified depending on the relative percentage of the framework grains like quartz, feldspar, and rock fragment. Similarly, the Wake group of sandstones, they are also classified depending on the relative percentage of the framework minerals of quartz, feldspar, and rock fragment. When the quartz grain, when the within the Wake group of sandstones, it is entirely the framework grains are entirely composed of quartz, that means greater than 95% in proportion, it is known as quartz Wake. When the quartz percentage comes below to 95% and the Wake group of sandstone composed dominantly of feldspar, then it is known as feldspathic grey Wake, or often it is known as arcosic Wake. Similarly, when quartz proportion is less than 95% and it is dominated by lithic fragments or rock fragments, it is known as lithic grey Wake. Now the term grey Wake, that is actually a field term. This grey Wake come from the appearance of this group of rocks. As you can see that it is a Wake, so that means it is rich in matrix proportion, so it gives a grayish appearance in field. So from that, in field we call them, or previously this gray Wake term was used particularly in the field, but instead of grey Wake, if you or if someone write feldspathic Wake or lithic Wake, that is also correct term for the classification of Wake group of sandstones. So this is how different rock types looks in hand specimen. This is a quartz arenite that is almost entirely the framework grains composed of quartz minerals having matrix percentage less than 15%. And this is the appearance of a arcosic arenite where feldspar is the dominant framework grain and feldspar dominates over the rock fragment. And this is the lithic fragment rich sandstone, which is called lithic Karenite. That means most of the framework grains within these sandstones are made up of rock fragments. And this is a typical Wake group of sandstone. You can see a dusty color or dark color of grayish color of this Wake group of sandstone. So from that, gray Wake term came into existence. So that's all. That's a brief idea about the sandstone classification. Thank you.